This is good because k minus j is strictly less than k minus j1. So we can do that. Therefore, just from the definition, we can conclude that v1 belongs to v of k minus j tau with mu alpha tau for alpha. Which is what we wanted to show. Okay, so that was just to give you a flavor of how this goes. You do some unfolding of definitions, you do some stepping, you examine what happens to the term as it runs. You know, using the operational semantics, you infer certain things. And then you use the induction hypothesis to say something about this term, stepping, etc., right? So that's the sort of flavor that these things have. And you do some step arithmetic along the way. Yes?
From the bottom line on the order there, and find the input test. So, so what do we need to know exactly to extract that from the operational semantics?
Okay, so we know here, we know that unfold gamma e. Well, so we're relying on the operational semantics of the determinant.
And multi value.
And multi value, yes.
And values being values.
And values being values.
Do we need anything more?
I don't think so. So yes, the proofs are tedious to recognize. Okay. Yes.
So this is just an observation, but one reason to maybe use the definition that as you defined it instead of using k minus 1 in the index is there, but it's much easier to use these proofs.
Exactly.
So.
And I was sort of looking ahead and thinking about that. Because otherwise, here we would have now, we would have only known something about this value, this v1 belonging to the set at k k1 minus 1, and then we would have had to do one more step of reasoning and something. Is there another question? No. All right. So I'm going to stop there with type safety. The proofs of lambda and application are interesting, but they essentially follow the rules of later. Okay. So what I want to do next is start observational equivalence, how you prove observational equivalence of programs. And what we're going to do in order to do that is we're going to start changing our logical relation. Right now, we just have this notion of when does a term behave like it has this type, right? A single term. We're going to move to binary logical relations where we talk about two terms belonging to a type, and we'll set up the definitions so that you only say that two terms are related at a type tau if they are in fact, contextually equivalent. Well, I mean, we'll set it up to capture the notion of contextual equivalence. And then we'll show that the logical relation that we set up is in fact equivalent to what contextual equivalence is. Actually, let me back up. I need to define contextual equivalence. So observational equivalence and contextual equivalence, some people use one term, some people use the other. Means the same thing. So the standard definition, so when I say that two programs are equivalent, what do you take that to mean? Okay, and how would I extend this notion to open programs or programs which have free variables? Should produce the same. Okay, so let me write down. So you're thinking in sort of you're already ahead in a sense and thinking in a logical relation sort of setting. That related inputs, you get related outputs. Let me write down the completely standard definition of contextual equivalence that has nothing to do with logical relations or whatever method you might use in order to prove equivalence of programs. Okay? So are people, when I say program context, does that, are people familiar with program context? So context is just any expression that has a single hole in it where you can plug another expression. So let's write down, let me back up a bit and talk about program context. So we've defined a notion of evaluation context up there, right? And we've been using it for essentially defining our operational semantics. But in general, let me use the letter C for what we call a general program context. A general program context should be any arbitrary program expression, any E, where you sort of take the E and you leave a single hole in it for where you can plug in another expression, assuming that the expression that you get afterwards is well typed. Okay, so here's the grammar for program contexts for, let's just do simply type lambda calculus for now. So here's a valid program context. Here's another one. Here's another one. Right, so we're just moving the position of the hole in some sense. If E, then E1, L, C, right? Let's consider what happens with lambdas. Here's another program context. So you can stick an expression under a lambda. We don't have evaluation context of this form, right? So this is one important way in which general contexts are different from evaluation contexts. Here, with application, okay, you have two positions, and so on. Same idea, full C, unfull C, and so on. Okay? So that's just the grammar for context. Now, when I say that I want to be able to take an arbitrary program expression and plug it into a context, I have some constraints in mind. In particular, I want to take a program expression of an appropriate type and plug it into a hole of the appropriate type, right? Because not all pluggings of context are going to make sense. They're not all going to be well typed. Okay, so let's define. Let's push this up. I'm going to write down a context typing judgment that will have this form. And I'll explain it in a second. Okay, so when we say that a context C has this type, we mean that the whole of the context, this is the type of the whole, and this will be the type of the whole of the entire expression after it has been plugged. So in particular, if you have a context of this type, and you are given an expression of this type, notice that this E has type tau under gamma, right, which matches the type of the whole. So if you're given an expression of this type, then once you plug the expression E into the context C, you will get an expression that has type tau prime under the environment gamma prime. Okay? So that's the way you want to read these typing rules. So I'm not going to show you typing rules for contexts in any detail. There's only a couple that are interesting. How would you write down a typing rule for the most basic context that we have for a whole? So let's say the whole has type this. Same thing? You could do same thing. Generally, it's better to allow, here you have to say that once you plug something into this hole, you get something of type tau. But in the simply type lambda calculus, we have weakening, right? So if a term type checks, if E type checks under gamma, then E will also type check under any extension of gamma. Right? So we're just going to build that in here. And that's a standard way of doing things. That at the whole, if you have weakening in your system, then you allow it here. Okay?
Are you looking for a syntax-theoretic presentation?
Am I looking for?
A syntax-theoretic presentation?
Yes. You mean for contextual equivalence?
For typing.
Oh, typing context, yes, yes. Okay, so in this fashion we can, this is this is our typing rule for the context, for the most basic context, which is a whole. And we can similarly define typing rules for all of the other contexts that we have in our grammar. Do you want to continue with that? It's really sort of a straightforward exercise. The main thing to remember here is that this is the type of the whole, and this is the type of the expression that you get after plugging in the whole, and it'll type check under this environment. All right, so this is the key bit. Okay? All right, so let's define contextual equivalence. Oh, there's actually, yeah. Okay, so we say that E1 is contextually equivalent to E2 at the type tau if, given an arbitrary program context C, okay, let's pause for a second. Let's do the definition of contextual equivalence for what we have on the board right now, which is simply type lambda calculus with recursive types. So for a language where programs may diverge. All right? Okay. So here we can say if you give me a context. Now, the idea is that I want to be able to plug in these expressions E1 and E2 into the context. So the whole of the context has to match this, right? The gamma tau. And the context has to be such that when you plug in the whole, you get a closed expression, okay, of some arbitrary type. I'll just write tau prime. So let's put a for all tau prime at the front here. So if you give me a context of this type, then if I plug C with E1, that terminates if and only if C with E2 does. Okay? Now, so does this make sense, right? Once we take the E1 or the E2 and we plug it in, this whole expression is going to be a closed expression, C with E1 or E2. It's going to be a closed expression of some type tau prime, but we don't even care exactly what tau prime is. We're just looking for termination. Okay? All right. Now, what if I was working in a terminating language? You would need them to terminate in the same value. So in particular, in a terminating language, you at least need to have a base type which is inhabited by two values, which is good. We have Boolean, right? So there, a standard definition of contextual equivalence would be pick tau prime to actually be bool, and say that CE1 evaluates to V if and only if CE2, well, should never have said, evaluates to V. So they must evaluate to the same Boolean. Okay? All right. Yes?
Quite what we want in a language with those main optional. So we have Booleans and recursive types.
If you have Booleans and recursive types, yes.
Would this still be correct?
This would still be correct. Yes. Except it's sort of unnecessary. You can generalize it.
So I think it depends on some quantifiers that you have with it.
Exactly. Yeah. The same. But this is just so much easier for me in a sense. can always write down some context where that observes the difference between them and then diverges or not. Right? All right.
How would you define quantities of values as the types of the
Sorry?
How would we define quantities of values in general?
Equality of values in general. So that's the thing. If you want to put values here and talk about equality, then you have to put a base point here. Otherwise, you're sort of back to the problem of well, how do you tell that two functions are equivalent? That's the issue. Okay. All right. So yes. Yeah.
So I was mentioning before, are these actual rules of the language just used to skirt call by value, or?
To skirt call by value?
Yeah. Call by value would reduce what's going to be applied to the value, and then you're going to reduce. So would this just take a turn?
So a context, well, I think, so the distinction that you want to keep in mind is the distinction between these general program contexts and evaluation contexts. And you're thinking about evaluation context a little bit, I think, there. Right? Because evaluation contexts define a certain order of evaluation, right? Left to right, call by value. And these contexts are simply, these are simply a formal device for us to say, hey, I have this massive software system, all right? And I want to change just this little component in it. Think of it that way, all right? So you have a massive software system. I'm writing down the whole software system, all of your code, except for this tiny little blob, right? That's where my hole is. This whole thing is my context, and this is where there is a hole. So this is just a device for anywhere in this entire program. If I were to take out one little component and replace it with another, assuming that that's well typed as well, right? That swap is well typed, what would happen? So it's nothing about evaluation order and so on. It's just a formal way of specifying what we mean by equivalence.
Okay, so this is meta-reasoning. This is not
Meta-reasoning. Yes, exactly. Yeah, I mean, you're thinking, what does this have to do exactly with the definition of the language, right? By definition here, I mean that to mean the stuff that I've been writing on the board in the beginning, right? Here are the terms of the language, the value forms, the evaluation context. Here are the, specifying the operational rules, and then giving the typing rules for the language, right? That basically tells us what the language is, right? So in that sense, it's fair to call general context a form of meta-reasoning because we're trying to formalize what we mean by equivalence. But it's very much connected to the language we are given, right? Because how did I come up with these contexts, which I've erased? I came up with them by examining the grammar for expression, E. Basically, for every expression that I have in my language, and I don't have all of them up there today, I write down a C that corresponds to every single E, right? Except when you have true and false, there's no subterm which you can replace, so to speak, right? So there's nothing to replace there. Does that make sense? Sort of? For now? Okay. All right. Okay, so here's what we want to do. We want to be able to prove that programs are equivalent. And we want to take contextual equivalence or observational equivalence as the formal notion of what we mean by equivalence. So let's see. What I want to do now is, okay, the language that we have right now just has recursive types, right? So here we could do some simple, trivial examples of equivalence. But the more interesting examples of equivalence come up when we start to talk about polymorphism and existential types. So in particular, when you add existential types to your language, you have the ability to define abstract data types. Everyone okay with abstract data types? Right? So like, for instance, a stack is an abstract data type, where you could implement the stack using a linked list or using an array. Right? Similarly, there are many abstract data types that we define, and what's interesting is that you write down an interface for an abstract data type, and you could implement it in different ways. So the concrete implementation that, or the concrete data structure that you use to implement it, for instance, may be different in your two implementations. And you'd like to be able to show that if you start out with your stack being implemented using an array, you can later swap that implementation out and replace it with the implementation of the stack that uses a linked list, which is going to be faster or whatever. Similar examples. So you want to know that you can replace one implementation of the interface with another implementation of the interface without affecting the behavior of the rest of the system. That's the basic point. And this is a really important concept, right, for software. It's modularity. It's how we implement large software systems and sort of reason about them in the best case. Okay, so if you could show that you have this implementation, if you could show independently of the rest of your system, independently of what's going on out here, I just want to be able to show that if I had some implementation E1 in here originally, let's say E1 is my stack implemented using an array, and I want to come in and replace that with an E2, I want to know that the behavior of my entire system is not going to be affected. I'm still going to get exactly the same answers, etc. Okay? All right. So that's what the definition of contextual equivalence is buying you. It's saying that if you can show me that E1 is contextually equivalent to E2, then you're good. Okay, but now the problem with this formal standard definition of contextual equivalence is precisely this for all C here, right? This for all C says that regardless of the context that you put E1 or E2 into, regardless of what's out here, in all possible contexts, you can swap E1 with E2. So in order to prove that E1 is equivalent to E2, this definition says, consider all possible contexts. That's not very helpful, right? That's a tough proof to do, and that's precisely why, so we always take this to be the notion of equivalence that we want, but proving it directly is really difficult, and often, it's not tractable in most cases. Some of it has to do with the fact that, one possible context that we're considering is this one, where you have a hole under a lambda and so on, but I won't get into that. So it's because of this quantification over all possible contexts that doing direct proofs of contextual equivalence or observational equivalence is not tractable. So what people do is that they use different proof methods that make it easier to do the proof, so where you don't have this sort of quantification over all possible contexts. So it cuts down the set of cases, these proof methods, they cut down the set of cases that you have to consider in order to show that your E1 and E2 are equivalent. Okay? So you use this alternative proof method to then more easily show that E1 and E2 are equivalent. And what you want from your proof method, whichever one it is that you use, you want that proof method, that definition, to be equivalent to this one. So if you've used that alternative proof method to show that E1 and E2 are equivalent, that should imply contextual equivalence of E1 and E2. Okay? So, in particular, the proof method that we're going to use is logical relation. So we're going to set up a logical relation. So just like we have a definition of contextual equivalence here, we are going to define, I'm going to write E1, and I won't put anything on this, to mean E1 is logically related to E2 at the type tau. Okay? This will be an alternative definition, and our goal is then, it'll be something that makes it easy to do these proofs of equivalence of E1 and E2. And what we want overall is to show that whenever E1 and E2 can be shown to be logically related to each other, then then that means that they are contextually equivalent. That's soundness of the logical relation. The logical relation is sound with respect to our definition of equivalence. So this implies this. And the reverse direction is completeness with respect to contextual equivalence. That would mean that any two programs, or program components, that are contextually equivalent are in fact logically related. So your proof method sort of handles, in a sense, all possible things. Okay? So we'll get to soundness and completeness later. Right now, maybe the best use of my time might be to just formally extend our language with polymorphism and with existential types, right? So that we're set up for next time. Okay. Oh, pull down the wrong book. Okay, so we are going to add universal types for all alpha tau and existential types, exists alpha tau. Okay, and I'm going to need to erase some stuff here. Are people familiar with polymorphism for the most part? Show of hands? Okay, good, excellent. All right, then I can do this quickly. All right, so since we have universal types, we want terms that allow us to abstract over type. So big lambda alpha E, right, type abstraction. And we need to be able to take expressions and instantiate them with types. So E applied to tau. Okay? Let's make some up here. Okay, so those are the intro and elim forms for universal types. We also need intro and elim forms for existential types. And we have there a notion of a pack where we pack a value, an expression. So pack tau E as exists alpha tau. And we need an elim form, which I'll put here. We need to be able to unpack values of existential types. So unpack alpha x equals E1 in E2. So if any of you are not familiar with the stuff that I'm putting up on the board, go in and read the relevant chapter of TAPL tonight. Okay? All right. What are the value forms that we want to add? So call by value language, standard thing. Value form for universal types? It's just like lambda, right? So type abstraction, lambda alpha E. Value form for existential types? Pack tau V, as exists alpha tau. I'm going to start writing pack tau V from now on and leave out the exists alpha tau. Yes. Lambda alpha E. Very good. Thanks for, okay. So lambda alpha E is a value form, right? Because it behaves like a regular lambda, lambda x dot E, in the sense that it suspends the computation that's under the lambda. Okay, so just like the term level lambda suspends this computation under the lambda, the type level lambda suspends this computation under it. So it's a value form. Okay? And then we want evaluation context, so type instantiation for pack. I won't write the as exists alpha tau, and for unpack. Unpack alpha x equals E. Okay? Extend our evaluation rules, our reduction rules. So once we have gotten, this, when we're doing type instantiation, once we've reduced this down to a value, it'll have the form lambda alpha E. We instantiate to the type tau, and that steps to E with tau for alpha. For unpack, once we have gotten this down to a value, it'll be something of existential type, so it'll be a pack. So we simply say alpha x equals pack tau V. That'll be the value form for the existential type in E, and that steps to this E with tau substituted for this alpha and V substituted for x. Okay? Now, I'm going to add a new typing environment, delta, which can be empty or have, or contain some type variables that appear free in an expression, and our judgment form changes. So just the standard thing. E now has type tau under a type environment delta that gives us all of the free variables, free type variables that might appear in E or in the type tau, and the value environment gamma, which maps variables now to types which may contain free type variables, but those free type variables have to appear in delta, right? Okay. So delta gamma lambda alpha E has type for all alpha tau if we can extend delta with alpha, and here again comma means disjointness, and under gamma E has type tau. For type instantiation, delta gamma E tau prime, let's say. So if under delta gamma E has a for all type, for all alpha tau, and if we have a type tau prime that is well formed under our environment, in our environment delta, then E applied to tau prime has type tau with tau prime for alpha. Okay, pack. Tau E as exists alpha tau has type exists alpha tau if what? Let's put the type thing first. Oh, I should use a tau prime here. Okay, if tau prime is well formed under delta, right, and E has what type? E has to have type tau with tau prime for alpha. Right? Sorry. Okay. All right. And finally, unpack. So delta gamma unpack alpha x. So these are E1 in E2 has some type. Let's call it tau prime. Actually, let's call it tau 2. If what? What do we need to know about E1? Yes, it has to have an existential type, so E1 has to have some type exists alpha tau. All right. And now if we want to type check E2, but E2 might have alpha and x free, so we add alpha to the type environment and x colon x colon what? X colon what?
Alpha.
Should x have type alpha? So coming back over here, right? X gets bound to this value v that's sitting inside the pack. The value sitting in the pack has type, this type here, right? But we want to keep the alpha bit of that abstract. So it's just going to be tau, this tau right here. Right? And notice that this is well formed now because even though this type tau has free type variables in it, alpha appears free in it, that alpha appears here. Right? Okay. Is that it? What do we need to know about tau 2? Tau 2 cannot contain alpha, yes? That's a critical bit. So I'll write that simply as, here I'm assuming disjointness, right? So alpha does not appear in delta, so I'll just say tau 2 has to be well formed under delta. But basically, yes, the important bit there is that tau 2 better not contain alpha, so that alpha cannot leak in a sense. All right? So we unpack this package, this thing that we have of existential type, and we use it in the context of E2. But we don't let the alpha leak, so to speak, right? The witness type. Okay, so that's just formally how we add polymorphism and existential types. Let's talk about a couple of examples now that we have that. So has anyone heard of free theorems? Theorems are for free. Yes, exactly. Phil Wadler's famous paper, Theorems for Free. So once we have polymorphism in our language, in particular parametric polymorphism, the way we're adding it, we can prove certain interesting things just based on the types. So for instance, the most famous free theorem, perhaps, the canonical one that everyone shows you, is suppose that we have some expression E that has the type for all alpha or alpha, right? The so-called polymorphic identity function. I don't know if everyone is familiar with this. Is everyone familiar with this? Oh, yay. Good. All right. So then I can just state it. So if we know that E has the type for all alpha, alpha, or alpha,